In this video, we are going to make a very simple introduction to the Kerr and Kerr-Newman black holes. The main feature of these families of black holes is that they have angular momentum. The Kerr black hole is analogous to the Schwarzschild black hole, but with angular momentum. It has no electric charge. And the Kerr-Newman black holes are analogous to the Reisner-Nordström black holes, but with angular momentum. So the Kerr-Newman black holes are the most general, and if you set the charge to 0, you recover the Kerr black holes. If you set the angular momentum to 0, you recover the Reisner-Nordström black hole, and if you set both the charge and the angular momentum to 0, you recover the Schwarzschild black hole. In a sense, it's the most general solution of the Einstein-Maxwell theory that describes a black hole. Now, it may seem that it should be relatively simple to add angular momentum to the Schwarzschild black hole, but as a matter of fact, it took 50 years after the discovery of the Schwarzschild black hole or the Schwarzschild solution to add this angular momentum. The first attempt by Lenz and Thüring really only achieved finding the asymptotic form of a metric, the metric of an object that has both mass and angular momentum, which is what actually most people would use in many applications, because the region closer to the horizon has become important only now that we know that there are black holes that have angular momentum. There is no simple derivation of this metric, of the Kerr metric. We are going to start by the Kerr metric. And you may imagine that if it took 50 years to discover this solution, there should be no easy derivation. In fact, the original derivation was based on the Petrov classification, and within this Petrov classification, in a search within a set of metrics, a family of metrics, which are called algebraically special. So this falls completely out of this course. We cannot really justify how to arrive to that metric from first principles, and we will have to content ourselves with this kind of heuristic derivation that was published by Tucholsky in a review which I recommend you to read just as an overview of everything that has to do with Kerr-Newman black holes. This reference, together with another review by Matt Visser, you can find in the program as recommended complementary reading. This derivation starts with this Lenz-Thüring asymptotic form of the metric, and it has pieces that you should recognize, okay, because this is the asymptotic behavior of the Schwarzschild metric. Okay, the R squared. Remember that in the Schwarzschild metric, this is 1 minus 2m divided by R minus 1. But obviously, if you expand for large values of R, you just you keep only the first term in 1 over R. This is what you get. Okay, so far so good. This could be the asymptotic expansion of any static metric of an object of mass m, okay, with a spherical symmetry. And the term that is makes a difference, okay, with this case is this one. Now I will explain what this parameter a is. Sine squared theta divided by r dt d phi. Okay, and this is an expansion for small values of m. I mean, this is a weak field expansion, so you can consider it is for large values of r, small values of m, and also for small values of a. Okay, so in fact this should be valid for up to terms of order a squared, which are not included. And a times m is the angular momentum in the direction c. Okay, so you only write j, but j is just the third component, jc. The other two components of the angular momentum vanish in this solution. Well, this is an approximate solution, which is only valid asymptotically. And you see that this metric is axially symmetric, not spherically symmetric anymore, because this term depends on theta in a way which is different from this one. And we proved that the spherically symmetric metrics are essentially of the form of the first line. So this second line breaks explicitly spherical symmetry, but not completely, in the sense that still the metric is invariant under transformations in which you shift this angular coordinate phi by a constant. The metric does not depend explicitly on phi, and then you can shift phi by a constant, which amounts to rotate the whole space-time around the z-axis. Okay, you have the z-axis, and phi is the angle measuring around this axis c. Okay, so this is the first piece of knowledge that you need. Okay, and the second also is an observation that if you want to describe an object which is rotating, you don't expect it to be spherically symmetric. You expect it to be flattened on the poles, just like the Earth. Okay, so maybe spherical coordinates are not the best coordinates to describe an object which is rotating. Instead of that, of those coordinates, one uses, or one may use, some coordinates which are called oblate spheroidal coordinates. The relation with the Cartesian coordinates a, x, y, and z is as follows. So instead of r, you have a square root of r squared plus a squared, and the angular part is really the same. Sorry, it is the same. This is cosine phi. Here you also have this deformation. Sine theta sine phi. And in the direction z, there is no deformation. Okay, so the deformation is in the xy plane, as you expect, in directions orthogonal to the axis of rotation, which is the axis c. So if you take the Euclidean metric or the Minkowski metric in Cartesian coordinates, and you rewrite it in terms of these coordinates, what you find is, I will just copy this from the lecture notes. You find something that can be written in this form. Okay, sigma divided by r squared plus a squared. I will define sigma in a second, minus sigma d theta squared minus r squared plus a squared sine squared theta d phi squared. Okay, here sigma is r squared plus a squared cosine squared theta. And you have to be aware that if you look in different references, sigma will be a completely different combination of r, sine theta or cosine theta, and a. Okay, but this is, well, you have dt squared, and the rest is just the minus dx squared within these coordinates, which probably are strange to you because you have probably never used them. The next step, following Minkowski, would be to rewrite this in the following form. It is exactly the same metric, but you write these terms combining t, dt, and d phi. And this term is minus a squared sine squared theta d phi squared Then there are two terms which are identical to the ones we have here, this one and this one. And the second term that involves phi and t is such that the cross term gives you vanishes, sorry, okay, because here in this metric there is no cross term, and only dt squared and d phi squared vanish, and this determines this second term uniquely. Okay, it doesn't take much time to check that these two things are equal, but it's just a simple calculation. Okay, if you now compare this form of Minkowski and this asymptotic expansion for the metric of our rotating object, this suggests you to make some replacements. For instance, you would like to replace this by some function of r different from this one, okay, because you have to get something like this. And you will also replace here in the r squared, this combination r squared plus a squared by some other function. In fact, well, keeping this sigma, because otherwise you would never recover Euclidean space or the Minkowski metric. You would replace this by another arbitrary function. In fact, you should do the same here. If you just replace the whole thing by an arbitrary function of r, you would never get back to this, because this depends on sigma being r squared plus a squared cosine square theta. So you just replace r squared plus a squared here by some function of r, and here by a different function of r. The moment that this is different from r squared plus a squared, the cancellation between that takes place in between these two terms of the crossed dt d phi term will not happen anymore, and you will get, or you should get, something of this kind, at least asymptotically. The replacement is as follows. So instead of r squared plus a squared, so let me get rid of all these things. Okay, and clean a bit. This blackboard would be okay to add here a function c of r. This is equivalent to changing this by an arbitrary function, and here you replace this r squared plus a squared by some other function of r, and that's all. Okay, then you can again calculate and rewrite this metric in this form again. This is almost like the original form, but there are some changes in a few places. Theta squared again, and minus r squared plus a squared sine squared theta d phi squared. So if f has the right behavior, so it behaves as r squared plus a squared, at least in some limit, all these p's that you have here in this line will go to Minkowski. And then there is an extra term, which is the one that depends on the function of r, which is c. And this is multiplying this. So here I have split this into this piece and the piece that depends on c. You can combine these two terms, I mean this one, and the one that remains is this one, which is the one that should behave asymptotically in such a way that as to give you this. Okay, so the idea is that now you plug this into you consider this your ansätz, Okay, this is the most difficult part, to find an ansätz that satisfies physical criteria and that may describe in the end something which is asymptotically flat on the one hand, that has angular momentum on the other hand, and okay, also mass. This is what you are searching for, and okay, in principle this ansätz is a reasonable thing to try. As Tukolsky himself says, well, he has used the definition of this oblate spheroidal coordinates, this parameter does not need to be a. Okay, it could be some function of a, because well, you expect that it depends on the angular momentum in some way, but it doesn't have to be a. So this is an assumption that well, has not been justified, and this is why this derivation of the ansätz is heuristic, and it is not as rigorous as you may expect. It has nothing to do with the derivation of the Schwarzschild metric that we did. Anyway, you take this ansätz, you plug it into the Einstein equation, you can follow the order that Tukolsky suggests to solve them. Okay, when I say you probably will never try, because this metric is far more complicated than any metric you have met before. Not only because it is off diagonal, it depends on theta in a new way. It also depends on, well, it doesn't depend on anything but theta, and it has this off diagonal term. So computing the connection, components, and so on is complicated. I may suggest that at some point you should try to become familiar with symbolic manipulation programs such as Mathematica, since Mathematica is expensive even for students with student license, at least for Spanish students, not in Princeton or so. There are other programs for symbolic calculations like Maxima, which give you, well, reasonable good performance for simple problems like this. There are not many packages for Maxima, so you have to make the definitions of the Christoffel symbols, curvature, and so on by yourself. This is good because when you use packages for Mathematica or Maple, well, those packages are made using the conventions of the guy who made these packages, and they may not coincide with your conventions, and well, and then you have to make changes everywhere. So you could try to do that, and as a trial for your program for Maxima, for instance, you can plug in this metric and impose that the Ricci tensor vanishes. Okay, the solution, I think there is a solution that is discarded because it doesn't meet the requirement. And the other solution that appears is that C is equal to 2mr, and F, which in many notations this is denoted by delta, is r squared minus 2mr plus a squared. And this metric that I just wrote here with these two functions, this is the Kerr metric, the Kerr solution in Boyer-Lindquist coordinates. These are not the coordinates that Kerr used to find the solution in the first place, but they are quite popular because they have very nice properties, and some calculations are simpler in them. Still, people use 2 or 3 different coordinate systems because each of them is better suited to different problems. So what are the properties of this metric? Some of them we have already mentioned, like asymptotic flatness, but let me review them following the lecture notes. Okay, the first thing to notice is that we set A equal to 0. This means that we are setting the angular momentum to 0. You just recover the Schwarzschild metric in the standard Schwarzschild coordinates. If you set M equal to 0, okay, in that case you see that C is 0 and F is just R squared plus A squared, which is what we had before introducing this deformation of the Minkowski metric. Okay, we had R squared plus A squared there. Then obviously we recover the Minkowski metric in oblate spheroidal coordinates. Then, well, you may have expected to get something with angular momentum but no mass, which would be a bit weird, but okay, it may be some kind of singular solution that one has to discard, but that is not what happens. You just recover Minkowski spacetime, and A doesn't have any physical meaning anymore because it is something that you can clearly remove by a change of coordinates. When you take R going to infinity, you just recover this asymptotic expansion that we wrote here with the length theory term, and which is what most people would use for a rotating, as the gravitational field of a rotating object at the moment you are at a certain distance from it, so you don't need to worry about the horizon or other effects of strong gravity if you want. An important property of the, or related to the Kerr metric, is that there is no analog of the Birkhoff theorem in this axisymmetric case. If you consider the gravitational field of a rotating star, okay, it is not necessarily described by the Kerr metric. Remember that in the Schwarzschild case, if you consider a spherically symmetric star, the exterior is automatically given by the Schwarzschild metric. Here, this is not the case. In principle, there may be many different metrics for rotating objects, which may depend on the different momenta of the mass distribution of this star. Okay? So we can characterize this the mass distribution of the star as by the monopole, okay, which corresponds to a perfectly spherical distribution, plus dipole term, quadrupole, and so on. And clearly, a star will have several of these momenta different from zero, and will characterize different stars. And the gravitational field will describe that. This is different from what you expect from the spherically symmetric case. Asymptotically, all these metrics, independently of the different momenta of the distribution, since all these momenta fall off at infinity much faster than the monopole term that falls with 1 over r, which corresponds just to the mass, you expect all these metrics to converge to this asymptotic form. The one that we have here, and then they are, you can say that they are asymptotically like Kerr, because Kerr also asymptotically has the same expansion that we wrote before. There is a complete difference if we don't consider stars and we consider black holes, okay, because this metric, well, we can advance that it will have an event horizon. So if there is an event horizon, if the star is not larger than the radius of this horizon, then the situation changes completely, because the only metric that has angular momentum and is axisymmetric and has a horizon, okay, is the Kerr metric. So this is a uniqueness theorem. And since you expect this metric to be the metric of a black hole produced by the gravitational collapse of any star that has arbitrary values of this momenta of the mass distribution, something must happen to these momenta. Okay, the gravitational field of the Kerr solution has different momenta. It doesn't have just the monopole momenta. You can find that it has more, but all of them have precise values which are given only by determined only by combinations of the mass and the angular momentum. These are the only two parameters that appear in the solution. An arbitrary star will have momenta of the mass distribution which are independent. They don't depend on two parameters alone. Okay? So what happens to the difference between the value of the momenta of the mass distribution and also the gravitational field in Kerr and the star? Well, they are all radiated away in the gravitational collapse process. This was first shown by Price, and this also led to the idea of the no-hair theorem that we will discuss later. The fact that these black holes, independently of the origin or the characteristics of the star they came from, or whatever mass distribution they came from, they are characterized by just a few numbers, the mass and the angular momentum, and when we add the charge, we consider the possibility of charge fields, also the charge, but nothing else. Well, since the metric does not depend on time and does not depend on the angle phi, there are two Killing vectors, which are ddt and dd phi, okay, the axial and the time-like Killing vector. Remember that there was a theorem by Hawking that was saying that stationary black holes would be either static or they would be axially symmetric. Okay, so this is the case in which they are axially symmetric. Asymptotically, this Killing vector you can check by taking, if you call this Killing vector k, you can check that k squared is larger than 0 when r goes to infinity, so it is time-like asymptotically, and phi is also a space-like asymptotically. But this doesn't have to be the situation globally, as we have seen in Schwarzschild or Reisner-Nostrom, for instance. So in relation with this, you can introduce a class of observers, which are called zero angular momentum observers, ZAMOs. And these ZAMOs, by definition, are those which have zero angular momentum. So the angular momentum, which remember, would be the quantity, conserved quantity associated to this Killing vector for a particle moving in this space-time. So it's something like this. Now this means that this is only phi, this alpha can only be phi, and okay, at least in these coordinates, and phi has two components, there are two components with phi that are different from 0 in the metric. One of them is phi t, and the other one is phi phi. Okay, so since this combination is 0, now if I compute d phi dt and use the chain rule, okay, I know that this can be written in this way, and well, this is phi dot divided by t dot, and this relation becomes minus g t phi and d phi phi, something that I can call following Poisson omega. Now this doesn't have to be 0. So even if your angular momentum vanishes, the angle phi can change with time, with the coordinate time. So you would be rotating, okay? And this phenomenon, which is called the dragging of inertial frames, and that has been experimentally tested with the gravitational probe B experiment, well, tells you that you cannot be just at rest even if your angular momentum is zero. Well, everything is due to the presence of this off-diagonal term g phi t, which is proportional to the angular momentum. So this omega, when r goes to infinity, you know what gt phi is, because this is the original expansion that we saw, and g phi asymptotically sine square theta r squared. So this asymptotically has this behavior. Okay, this is an important relativistic effect. Now, instead of zero angular momentum observers, CMOS, we can consider and study static observers. Static observers have, by definition, a velocity which is proportional to the time-like Killing vector. So, since we know that x dot the square, this is g mu, x dot mu, x dot nu, this has to be 1. Well, this determines x dot mu to be k mu divided by the absolute value of k. Well, this kind of motion that we just defined doesn't have to be a geodesic motion. So to follow this motion, you will have to use your rockets in your spaceship or something like that. Okay, but this is not important. What is important is that this is good as long as this doesn't vanish. Okay, we just saw that the time-like Killing vector k squared, well, it's time-like at infinity, so it has some positive value. But okay, it may happen that just as in the Schwarzschild metric, when you move to smaller values of r, this k vanishes and maybe even changes sign. Okay, so when this happens, so when k squared, which is equal to gtt, is equal to 0, you arrived at the what is called the static limit. Beyond the value of r for which this happens, there cannot be static observers. We know what GTT is. Okay, it's a quotient. We just have to look at the numerator of this quotient, which is r squared minus 2mr plus a squared cosine squared theta, and this vanishes. The place where this vanishes is the static limit, and there are two roots for this second order equation. So let me call it plus and minus. R is a function of theta, and this function is m plus and minus the square root of m squared minus a squared cosine squared theta. We will see later what this surface is like. Beyond this, you cannot be static anymore. This should remind you a bit of what happens in the Schwarzschild metric. Okay, we didn't discuss it in this way, but it's the same. Beyond the horizon, you are not static anymore. Okay, you move, and you move into the direction of the singularity. Okay, then knowing that this limit exists, one can define a region which is called erosphere, which is the region where what we said, well, where there cannot be static observers. So it corresponds to this region. It has an exterior limit and an interior limit. Okay, in this region, well, you can check that GRR is larger than 0. This can be seen by studying the relation between f and this function here. Okay, f is like this, but cosine squared theta replaced by 1. If you factorize this expression using these two roots with plus and minus, then you can see the regions where this is positive and negative, and you see that f will be negative exactly in this in the region between these two roots. So GR is larger than 0, and you cannot consider R space-like anymore. Well, this region is very special. Well, the fact that there are no static observers there, that they have to move. You may think that this is the horizon. It is not the horizon, okay? And this is why we call it the ergosphere. And in this region, we will see that this region is outside of the horizon. So you don't need, you can enter into the ergosphere without entering the horizon, enter and leave. There is this Penrose, so-called Penrose process that Penrose conceived as a process to extract energy from the black hole. Okay, we are not going to review it. I think you can read it in many places. This is a classical process, and it has a quantum mechanical analog, which is the phenomenon of super radiance. Again, you can extract energy from the black hole in this way. So we have considered Deimos, static observers, and now we are going to consider another class of observers which are called stationary observers. Which are observers that move with some constant angular velocity measured in the coordinate time, and that we call omega. But it doesn't have to be exactly the same omega that we wrote before. Okay, let's consider stationary observers moving with constant radius, and also in, let's say that we consider them in the equatorial plane. Okay, so in this case, these observers have a velocity that has only components t dot phi dot 0 0. Maybe not in this order. Okay, it doesn't really matter for what we are going to do, but still. Okay, if we write this in this form, we know that this is going to be t dot k alpha, because k alpha has components 1, 0, 0, 0, 0, so the coefficient would be t dot, and this is phi dot q alpha. And now remember that d phi dt could be written as phi dot over t dot, and this means that phi dot is equal to omega t dot. So if we substitute this here, we have that this is t dot, a common factor of k alpha plus omega q alpha. Now we impose the Marshall condition that u squared has to be 1, and then this will be t dot squared, and well, the absolute value or the norm of this vector squared. Okay, so t dot will be 1 over k plus omega q, the norm of this vector. Again, the same reasoning as before tells us that you can do this, so you can have this class of stationary observers as long as this norm is different from 0. In fact, since we started with the square, and this is how you compute the norm, and this is the square of a real number, this has to be positive, so you cannot allow it to become 0 or negative. Okay, and okay, so this can happen if this condition, which is equal to k squared plus omega squared q squared plus 2 times omega k q, this is larger than 0. And now if we replace k squared by g dt, q squared is g phi phi, and the product of k and q is g phi t, or dt phi. Okay, this gives us a condition for omega, because well, this could tell you what are the allowed values of omega depending on the position in the space-time, because depending on this position you will have certain values here, and this may be or maybe not solvable for a real value of omega. So what you have is, now I simplify this expression, okay, just a second order equation. So you will get this plus and minus, same expression again, g phi phi squared minus d dt divided by d phi phi. Okay, just following Poisson, we can call this omega, and this omega is nothing but 2 mar divided by r squared plus a squared minus f a squared sine squared theta. This is called sigma in Poisson, so just be careful with what sigma means in each place and each reference. And the result is that the allowed values of omega, okay, this would be omega plus and omega minus, are that okay, omega is takes values in this interval, and omega plus minus is omega plus minus omega squared minus g dt divided by g phi phi. Now, clearly, outside of the static limit, omega can be equal to 0 if you want. This is a possibility. So if omega is can be 0, this means that omega minus and omega plus have to be negative and positive. But certainly at some point omega minus changes sign. Okay, it does so at the static limit, what we have called the RSL plus. Okay. Well, when this because you can check that when you move inwards towards smaller values of r, omega minus grows and omega plus decreases. Okay. So at some point you will find that omega plus is equal to omega minus, and this will be the only allowed value for omega. Well, this happens when f is 0. And since f is r squared minus 2mr plus a squared, then you find that this happens at these two values of r, which are m plus and minus square root of m squared minus a squared, which is an expression that familiar from the Reisner Nordstrom black hole, but now with q replaced by a. Okay. Well, and the only possible value then, this is the value of r, the only possible value for omega is called omega h. and it's called omega h because r plus will be the horizon, okay, and r minus will be this Cauchy horizon. So this will be the value of omega at r plus, okay, and this happens when since this you look here, and we said that this happens when both omega pluses are and omega minus are equal, so this must vanish. So this is really the value of small omega, and you can check that this is just a divided by r plus square plus a square. Okay, omega is an angular velocity, and if r plus is the angular velocity, sorry, r plus is the place where the event horizon is, omega h is then the angular velocity at the horizon, the only allowed velocity for stationary observers, and this is interpreted also as the angular velocity of the horizon of the black hole. Then, well, the next thing is that by construction, remember that we were exploring the norm of this vector. Okay, when you arrive at the horizon, and you evaluate this at r equal to r plus, well, this vector must be null there because the norm vanishes. The norm vanishes at r plus and r minus. And then, since this is a Killing vector, because it is a combination of a Killing vector and another Killing vector with a real number, and this is easy to show that it is also a Killing vector, well, this is the Killing vector such that its Killing horizon coincides with the event horizon, which is one of the properties that we said happen for stationary black holes. This is a stationary black hole. It is not static, okay, because there is this t phi cross term, and this t phi cross term means that the vector k is not hypersurface orthogonal. You cannot remove it. Okay, so instead of studying the event horizon globally in the maximal analytical extension and so on, we can study many properties of the horizon just looking at the properties of this Killing vector, okay, which becomes null at the horizon. Okay, singularities of the metric. Well, clearly the metric is singular whenever sigma is equal to 0. There are several components in which the sigma appears in the denominator. Sigma, remember that was r squared plus a squared cosine squared theta, and this can be 0 if r is 0 and theta is equal to pi over 2. And you can check that the Kerr-Newman invariant vanishes for this value of r and sigma. What kind of singularity is this? Okay, well, r equals 0 is not a point. R equals 0 is really a circle or a sphere, because if you look into these oblate spheroidal coordinates that we introduced at the beginning, if you set r equal to 0 here, well, for a fixed value of theta, which is pi over 2, these signs are equal to 1, and okay, the cosine is 0, you are in the equatorial plane, and this describes a circle of radius r, not just a single point. Okay, this singularity is often called the ring singularity of the Kerr-Newman black hole. It is beyond r minus. R minus is a positive value of r, r plus is a positive value of r which is larger than r minus, and r0 is much smaller. So if you remember what we said about the instability of Cauchy horizons and all the problems and the pathologies that happen there, you expect that this singularity will not be there. Really, there are very funny properties inside of the region R minus, R equal to R minus in this space-time. Well, the other singularities that you find are where f is equal to 0, because f was also in the denominator of several expressions, but we just said that f equal to 0 corresponds to the two horizons, and in fact you can show that there are Eddington-Finkelstein-like coordinates which extend the metric to the horizon, across the horizons to the interior, so the metric is regular there. We can already draw a diagram of more or less what this space-time is like, of my drawing power, so I'll try to do it as best as I can. This is the axis of symmetry and also pointing in the direction of the angular momentum of the rotation, so rotation takes place in this direction. This represents the event horizon R plus. This represents the horizon, the Cauchy horizon R minus. And this represents the, well, this is not exactly yet the ring singularity, but this is the surface R equals 0. Then here we have to, the equatorial plane is over here, so the ring singularity will be these 2 points, okay? And now you rotate this diagram around the axis as shown here, while these 2 points generate the ring. We still have to draw the ergosphere, so this is next. So this is the static limit plus, okay, which is a function of c. You see that it touches the event horizon at these 2 points, and then the limit, the interior limit is more or less as follows. Okay, this will be RSL of theta minus, and you see that it touches the surface R equal to 0 at the ring singularity. Okay, so in between this blue surface and the green surface, there is this ergosphere where there cannot be any static observers. Okay, this has been taken from a book which contains all everything you want to know about the Kerr geometry and maybe more. A book by Barrett. Barrett O'Neill, which is published in Dover, and I think it is a book. If that could be the reference if you want to know very detailed properties about geodesics, maximal extensions, and everything else from a quite rigorous mathematical point of view, and it's just a whole book dedicated to this. Another property that you can also find in this book is that when you are inside R minus, so in those whole region here, well, if you take any two events, P and Q, there will always be a future pointing time-like curve going from P to Q, no matter what P and Q are. This means that there will also be a future pointing time-like curve going from Q to P. This means that this whole space-time is sick. You cannot time-orient it or anything, okay? And you can construct time machines and do all kinds of crazy things. This is one additional reason why you may want to get rid of all this region inside of R minus. Also take into account that the instability of the Cauchy horizon, okay, which is here, is a reason for not trusting too much the interior of the black hole. Okay, this is related to the strong cosmic censorship conjecture of Penrose, as we have said. And okay, there is no more time to say many more things about the Kerr black hole. Probably all you want to know, apart from these general properties, unless you want to study it more carefully, the most important thing would be the asymptotic expansion, because well, this is not really a property of the Kerr black hole, but it's a property of any star. If you want to incorporate the effect of the rotation of the sun to all the solar experiment or solar system experiments, well, you just want to take this into account. It's a weak field. If you do the experiments almost anywhere, is always far away from where the horizon would be. But this is not the same as taking the Kerr metric outside of the sun. It's just saying that the asymptotic behavior of the gravitational field of any rotating object should be like this, including the asymptotic behavior of a black hole. So this is the common asymptotic behavior. Well, I failed to mention also, before I close this video, that well, there are horizons if A is smaller than M in absolute value, and well, when M is equal to A in absolute value, these two horizons coincide. This is the extremal Kerr black hole, and well, when the A is larger than this, there are no horizons anymore, and this singularity would be a naked singularity. And what about the Kerr-Newman black hole? I'm not going to write the electromagnetic field, but this electromagnetic field on top of charge will have a magnetic dipole momentum, which is due to the fact that there is rotation. And as for the metric, well, you only need to change f, okay, this function f in the metric. So C is exactly the same, and F, I will write it here, F, instead of being just this, has an additional term, Q square. So just like this, very simple. And all the properties that have to do with extremality now will depend on this function here. You get this additional factor. Remember that this comes from the vanishing of f, which we have here. So qualitatively, the properties are not too different. When Q is 0, you recover the Kerr black hole. When A is 0, you recover the Reisner-Nordstrom black hole, and so on, as we had announced. And this is more or less what we can study in this overview of the Kerr black hole.